My name is Lorie Srivastava. I am a postdoc at UC Davis working with Hugh, Emma, Nicole, Frank, and some other folks. Jose Sanchez, who's also with the Forest Service down in Riverside. Chloe Grenache, who's at Michigan State as well, and I'm probably forgetting several people right now, but I have them all listed later, so I like to list them. So I'm going to talk about in a little bit more detail about the economic valuation work that I'm doing. It's with very similar ecosystem services what Emma presented, but slightly different. So Hugh's done a good job explaining, the motivation, and he was the driving force behind the project. So I'm not really going to talk about that so much, other than to highlight liability considerations are sort of something that's become important, as you mentioned. And so we have to be careful about how we value these different ecosystem services because they do need to stand up in a court of law. And I don't know that these values that I'm estimating necessarily will be the ones that will be used, but they're a good sort of first cut in helping managers of the Forest Service sort of figure out where priorities might lie based on how these ecosystems, the value of the ecosystem services are reflected in the economic values. So it's a basic research question. What is the baseline economic value of the ecosystem services I'm looking at, and how will climate change affect these values? So how will they change over time? So I'm estimating a value baseline, sort of present day value, as well as mid-century and end of century. So study area everyone knows, so I'm not gonna, it's just all the 4 national forests in Southern California. Lots of people, big areas, climate challenges. And one thing I do want to point out is the number of people. So for economists, when we value something, we do it relative to human values because we're interested in how something affects human welfare. How better off or worse off will we be? So since it's an area that in which a lot of people reside here in Southern California, if we estimate a value per person, it's going to be very large because there are a lot of people in the area. So the idea behind linking economics with the ecosystem services is the Millennium Ecosystem Assessment, which sort of did a nice job of laying out, here's how these 2 things are linked. So the way I like to think about it is the project basically goes in 2 steps, 2 phases. The first phase is estimating the quantity of the ecosystem service. That to me is like the biophysical modeling that Emma and others have been involved with. John Kim with the Forest Service in Corvallis, his model, he's developed a model or a modified MC2 model for our study area. That's a large input into the work I'm doing. So that's the first phase, and that to me is the supply side of things. What's the supply of the ecosystem service? That's what's the quantity. Then there's the demand side. How do we as people or households, individuals here and elsewhere, how do we value these ecosystem services? So that's the demand side. So there's demand and supply. And I'm going to be using different methods to estimate the ecosystem services depending on the ecosystem service in question. So this is one way to think about it. Michael Hand, who's my co-PI with the Forest Service in BC, he has this nice sort of graphic he developed for a presentation we did elsewhere. That we have some climate, we have a natural asset, these national forests. They provide a stream of ecosystem services to us. They're affected by climate change, either in quantity, so they decrease in quantity, or by quality. You could think of water quality being affected, for example. So some change, and that change either increases or decreases human well-being, or what we call economic utility, and that's what we're going to see. So the first part, like I said, that's the biophysical ecological model, spatial modeling that's being done, and then this part, the part that affects how well-being is affected, that's being measured by the economic work. So these are ecosystem services I'm looking at: carbon sequestration, water provisioning, sediment retention, air quality, recreation services. And these are the different methods I'm using. There's been something called benefit function transfer, which I'll talk about in a second. Demand modeling, which I'll go into later when I talk about water provisioning. Cost function for sediment retention, air quality, which is sort of multiple kinds of models. And then Frank did a really nice job yesterday, of course, talking about recreation services using a random utility model, demand model. So Frank covered this yesterday, and this is, I think, a challenge for economists in general, sort of trying to explain what economics is. And when I've taught economics classes, everyone's like, first day out of class, what's the definition of economics? Everyone's like, it's about money. And I'm always, it's a study of values. It's not a study of money, it's a study of values. How do we value something? Whether it's a commercially available product or not. What values do we place on it? And all of our values are different. My value for clean air might be different from your value. So, we basically are trying to average these values out. And with that value, basically reflects how important we feel an ecosystem service is to our well-being. So one thing I'd like you to keep in mind is economic value is not equal to cost. And Frank explained that yesterday as well. So it's not how much money I pay for something. That is not the economic value. If you buy, I usually use water as an example just because I'm doing water later. If you go to a store and you buy a liter of water, and I don't know how much it costs, let's say it's $2. So you're willing to pay at least $2 for that. If you don't pay that $2 and you're not willing to pay it, that means you value it less than $2. It's not worth it to you, right? Maybe you'd only pay it $1, but you're having to pay $2, you're not going to pay it. So it's not worth $2 to you. For those of us who do pay the $2, it might well be worth $4. Let's say it's super hot outside and you don't have your regular water bottle. You go into a 7-Eleven or something and you buy it. You might be willing at that point to pay $3 or $4 for it, but you only have to pay $2, so that's fine. So, but that's a cost. That's something you pull out of your wallet and you're paying. That's not a benefit to you. The cost you pay for it is not the benefit. The benefit is, when you get your thirst quenched by drinking the water. That is the benefit. And that benefit to you should be worth more than $2. If it wasn't worth at least $2, you wouldn't pay for it. But keep in mind when people or you go like to Costco or wherever, you're buying a flat of water bottles, bottled water. That's a fraction. I mean, what you would pay at home out of your tap is a fraction, like pennies, like not even pennies, less than pennies for what you pay for a glass of water out of your tap. But so we all pay, really low rates, but we can tell people value that drinking water much higher because think of all the people who are going around buying bottled water or have like purification systems in their homes, right? It's worth a lot more than what people pay from their water bill. So here's a conceptual way to think about it. We have ecosystem services that are provided by the National Forest. There's some kind of climate change. I'm going to look at mid and end century, what climate change is. The ecosystem service is changed by either quantity or quality. This is measured by the biophysical models. And then I'm going to measure how does this affect people, and that's going to be reflected by the economic work. So what's the future going to look like? I'm trying to do baseline and mid-century and end of century. What will the climate be? Is it going to be crazy, insane, with like robots out of control? Is it going to be a crazy future? Or is it going to be great with robots in love and rainbows? Like, how good or bad will the future be? I don't know. None of us know, right? So the method I'm using is basically running estimates under 3 different possible climate futures, and we talked about that yesterday. Hot and wet, sort of ensemble mean, and a hot and dry future. Those are the bookends under certain assumptions of how proactive or not policies will be. So we're assuming sort of worst case scenario, high population growth, low income growth, slow income growth, so almost like a worst case scenario. So I'm basically going to try and monetize ecosystem services, and I'm going to apply discount rates to these values, and I'll explain that in a second more. So I'm going to talk about carbon sequestration first. So I'm using the biophysical work is being done by John Kim in Oregon, Corvallis. He's got an MC2 model, which is a dynamic vegetation model. So it's going to predict how the vegetation changes over time, which will then sort of tell us how carbon will change over time based on the vegetation. The economic method I'm using is called something called benefit unit transfer. Basically, I'm taking a value, a monetized value from someplace, and applying it here in Southern California. And it's called social cost of carbon. And the reason, and this is something that gets criticized in economic literature a lot, if I take a value, say from Paris, France, and then I'm applying it to Los Angeles or whatever the thing I'm looking at, it's like, well, the conditions in Paris and people's preferences, willingness to pay in Paris for water, for example, might be very different from people from LA. So it would not be suitable or correct, or you could, but you have to make huge caveats that, this might be high or too low, etc. But in the case of carbon emissions, it's different. Carbon is global, it's a global cost. So the unit that's the dollar values has been monetized by the US federal government applies to carbon emissions globally. So it's okay to use this value. So the idea, there's lots of social costs of carbons, and Hugh alluded to this. So why this one? And as I said, if you look at the literature, this is probably one of the most it's one of the ones that people use a lot because it's pretty rigorous, and they were updating it every few years. So that's a big advantage of this, that it is being updated because values change over time. The modeling, by and large, improves over time, and so that was the reason that people liked it. So there are 3 general circulation models that underlie this. They're pretty, they're 3 the best well-known: Fund, Page, and Dice model. And the interagency working group basically just averaged these values. So this was the interagency working group set up under the Obama administration, coming up with, there's lots of folks at the table who are working on this. And they were, at first ones came out in 2010, the estimate for the social cost of carbon, and they continuously updated in 2013, 2015, and that's the last year they provided results, because under the new administration, the group was disbanded. But I'm going to still use the value. So here are the values. This is just, from their report. These are $2,007. I want you to keep that in mind. It's not 2017 or 2018 dollars. So these are the years. So they basically did them out to 2050, and these are different values. I'm going to explain the discount rate in a second. So these are different values. For example, the closest one, 2020, would be like $12 or $43, $65, $129. Now these are very different values. So, and to Emma's point that depending on the discount rate, that's what I explained the range. So the discount rate is, if you are looking at today and you're thinking about the future, how worried are you about the future? Are you really worried about it or not? If you're like, things will work out, someone smart engineer will figure something out, I'm not really worried about it. In that case, you're discounting the future quite a bit. You're going to use a higher discount rate, say 5%. And so this is why you're not worried about the social cost, you're not worried about the future. Social cost of carbon is fairly low. At 3%, and the 3% is sort of generally what most economists will be using right now. They'll do both 3 and 5%. This says, I am more worried about the future, not sure what's going to happen. Greenhouse gases are a concern. So this is what you value social cost of carbon at, $43. So, and then similar to 2.5. This last column is the 95th percentile. This is basically saying they estimated, what if things go really off the rails, really things go awry, we're not really sure what the future is going to be like. If that's the case, they've estimated the value, and that's what's at $129. So here, it's like, what value will we use? So what I've done is use different discount values based on the climate future we think might be realized. So these first are just the actual preliminary findings from the MC2 model that John has developed under the different climate scenarios. And so you can see here, 2050, these are just how this will change relative to a baseline. So you can see under a warm and wet future, it's going to increase both by mid-century and end of century. The quantity of carbon is going to change. And what he's done is he's provided different pools, carbon pools, above ground, below ground, live dead, as well as soils. But I've just pulled it all together across all 4 national forests. So that's on average, we think it's going to go up by about 20% or so. And by the end of the century, over 50%. If we have an ensemble mean, things are sort of in the middle, not a lot of change across the 4 national forests. Hot and dry future, it's going to decrease by quite a bit.
Do those use his new calibrate with the new fire data that he's using?
No, so I was just about to say that. We're expecting new results literally any day now, but these were the last ones he sent. So that's why I'm saying preliminary. I don't expect the direction to change. Like, I do still expect the hot and dry will still be less than the baseline, etc. How much these will change by, the actual numbers, I expect to be different, but the direction would be the same. So that's carbon. I'm going to have a sediment retention now. So if you think about the mudslides here in January, it was horrendous. There's value people place on the sediment that gets eroded off the San Gabriels, for example. So we know there is value to that. The removal, they don't want those. So that's what we're trying to estimate. So what I'm doing here is I'm taking a different approach. There was John Loomis, actually Pete Wolmuth, who was here yesterday. He and some others at the Forest Service wrote this article back in 2003 where they estimated the average cost of sediment removal from the San Gabriels by the LA County Public Works Department. And they work with folks at the Angeles to come up their estimates. It's a nice little paper. And so the idea is I would like to replicate this paper, but also extend it. So in theirs, I think they estimated the average cost in, I want to say $1998 was, I think, $12 something. So as they say in their paper, the San Gabriels are the fastest growing mountains in the US, and they release the most sediment. They have debris basins that collect the sediment, in which the sediment is collected, but these debris basins really are to collect the water, as he was saying, about 30% of the local water, or of water here in the region comes from local sources. A big portion of that is from the national forests. So they try and keep these debris basins clear so when the rains come, they can fill up with water. Now the problem is, as the debris comes down, they got to go dredge it out. And if you have a fire, so all the vegetation cover is gone, and then a rain event, significant enough rain event, you get tons of sediment coming down, and they have to go in and, you know, over emergency sort of protocol and remove the sediment. So for this study, I'm going to focus just on the Angeles National Forest for data constraint reasons. There are 41 watersheds in San Gabriel Mountains that are of interest to us. We have cost data from LA County Water and some cost data from, sorry, I should say Public Works, and we have about 37 years of data. I'm going to estimate two models. The first one is a sediment model, say how much sediment is going to come down. I'm going to try and predict that for mid-century and end of century. The second model is I'm going to try and monetize that. Instead of using an average cost, you sort of think about this intuitively. You think the first 1,000 cubic yards that they're going to remove sediment, the cost for that first 1,000 cubic yards is going to be different from the last 1,000 cubic yards. So you can think over the amount that is removed, the cost will change. So hence where I'm going to estimate a function, and that will vary based on how much is being removed. And again, I'll do these estimates to mid and end of century. Water provisioning, I just have a few minutes. So water provisioning, a little bit different from what Emma had said about recharge, and I'm just doing water, and I'm assuming it's surface water, not groundwater from the 4 national forests, and I'm going to estimate the use to urban users. So I'm not worried about agricultural users or industrial users, just to people in their household. When you open a tap, what's the value to you for that water? When I first started doing this, and I have to say I really like water studies, and so I was like, oh, this is great, and this, there's so much problems with, in Southern California with water. There'll be tons of willingness to pay studies, and I didn't find a single one. I looked and looked, there's none. So that sort of put a kink in what I was going to do. Ideally, I'd have a budget to do a survey, but there's no budget, and it takes quite a while to do a survey. So instead, what I'm going to do is leverage existing water demand studies and use the relationships that they've estimated of how when prices change, prices go up, people generally will consume less water. So they've estimated that relationship, they've quantified it. So I'm going to leverage those values and use it for my study. Again, I'm going to look at how quantity changes over time, how that reflects in people's value of that water, when the quantity changes. Air quality. Oh, this didn't come up quite as nice. So this is basically a picture from the LA Times of Ventura County during the Thomas Fire. Yeah, so that's how bad air quality becomes. So this picture was in December 2017. So we know people value clean air, obviously, and so I'm going to estimate this using a couple of models. I'm getting spatial estimates over time. Oh, whoops, wrong one. There we go. Couple of things. You think about the national forest, there's sort of two things that are happening here. We've got nice large green spaces that remove pollutants from the air. That's really nice, improves air quality. However, when there's a fire, air quality diminishes and there's spikes. It just goes down dramatically. So the problem here is, what's the net effect of the green space of the national forest? So what I'm trying to estimate is how it the economic value changes relative to human health, because that's what we're looking at. I'm using 3 models. First, I'm getting data from John's MC2 model, which is going to feed meteorological data. That's going to feed into iTree, which a U.S. Forest Service model developed and kept by Dave Nowak and his team, Syracuse. And that iTree model, basically says in an urban area, how much pollutants do the trees remove from the air? So I'm going to have meteorological data from MC2. It's going to go into iTree. iTree is going to say, okay, this is how much pollutants removed by the shrubs and the trees. And then I'm going to put that into an EPA model called BenMap, which will estimate the economic value. And it's done by human health, and it does things like labor productivity, hospitalizations, and I think it's being varied by ages, like if a young child who has asthma goes into the hospital versus an elderly person. So this is a really nice, confusing diagram of my process, which I'll just skip. And now we'll just get summarized. So, and it's 9:15, so I think I'm good for time. So what's going to come out is, so I don't have a lot of results to present at this point, partially because I'm waiting for the MC2 modeling results, which are going to be available just apparently by the end of the week. So if this conference had been next week, I could have presented something. I think what's going to come, based on some preliminary data we got, some things are going to be good. They're going to be as we expect them to be, which is good. And some things might come out in unexpected ways, which is also good. So, you know, I think out of all of it, and I think Emma did a nice job of presenting this, is that there's sort of 2 key things about the project, how it's gone, is that the biophysical modeling and the economic valuation work are really twined in together quite closely. And the challenge has been throughout is, you know, making sure the estimates are reasonable and something that people, like when you try and explain to people, that they can trust as well. And again, this is something of great interest to the Forest Service for liability purposes. So again, it's something that, you know, needs to pass a rigorous inspection. So I think the results are going to be really exciting, and there'll be more to come.